Assalamualaikum and very good morning to my panel. My name is Muhammad Hafizuddin bin Hashim with student ID 2019601622. Today I will presenting my final year project proposal with title Compressive Behavior Investigation of Silicon Rubber based on Hyperelastic Constitutive Model. Before I start my presentation, I would like to state that I was changing my simulation from ANSYS to Abacus software. Project summary. Designing silicon structure for modern and safe application leaf buffer is complex due to its highly non-elastic behavior. The elastic, hyper, and viscoelastic properties are the essential material properties in constructing such components. Thus, to aid in designing a leaf buffer, it is vital to understand the deformation behavior of silicon material under compression and impact. This project will investigate the deformation behavior of buffer component made of silicon material under compression and impact tests using a numerical approach. The initial stage will include developing non-linear finite element model to simulate the deformation behavior of buffer components accurately using commercial software Abacus 2021. Design of experiment will be applied to set up the essential specimen parameters. The second stage will involve an optimization procedure based on response surface methodology using commercial software, design expert, outputs and results will be analyzed and compared. The outcomes and findings will be reported. Next, introduction. The project primary goal is to enhance the qualities of leaf buffer. Leaf buffer are safety measures that technicians must install at the bottom of an elevator shaft to ensure the safety of passengers. Similarly to any other safety equipment, leaf buffer must comply with several criteria, the most essential of which is the buffer method to bring an impacting elevator vehicle to a stop. Since the inception of elevators, a variety of safety devices has been implemented to ensure that the elevator does not fall out of the building or collapse. The elevator operating velocity and mass are considered while specifying the buffer for the elevators. The fiber to be reinforced was arenga pinnata. The sugar palm plant is gaining popularity due to its ability to provide high-quality sap for manufacturing of alcohol fuel. Arenga also possesses outstanding mechanical qualities, resulting in long lifespan. Sugar palm waste have the potential to be used as fibers and filler in polymeric composites. This research set to determine the mechanical properties of arenga pinnata biocomposite as a potential leaf buffer substitute material by using a simulation technique combined with a compression test inside the Abacus software. The material constant of two hyperelastic constitutive model, the Neo-Hooken constitutive model and the Mani-Rivlin constitutive model, were determined using their respective material constant. Based on the review, it is found out that leaf buffer confront challenge during impacting elevator vehicle to rest, limiting its performance. Most of the problems faced are stemmed from the material selection of a leaf buffer. The substance affects its performance for a better impact. For literature review, filled silicon rubber are increasingly being employed as engineering material in automotive and biomedical applications due to their strong mechanical qualities, excellent resistance to harsh conditions and temperature, and good biocompatibility. The constitutive relationship serves as the foundation for the investigation of the mechanical properties of rubber material when determining the constitutive relationship of superelastic material. It is necessary to consider the geometric nonlinear relationship of superelastic material. However, assessing the appropriate hyperelastic model for the accurate prediction of the linear-nonlinear mechanical behavior of polymer is a challenging matter dependent on the chemical composition and physical response of the polymer and the fundamental understanding of the mathematical formulation. In the definition of biocomposite, it is a material made from a mixture of a materials such as resin and natural fiber that are either wood or non-wood that act as a filler and are derived from plants. The author evaluate the characteristics of silicon biocomposite material in the study of silicon biocomposite material and how it contributes to the optimization of the performance and qualities of a material. This will be related to its application, as it will be widely employed in the future. The advancement of this technology contribute to reducing environmental pollution, the improvement of the material mechanical qualities, biodegradability, and aesthetic look. In addition, the wide range of physicochemical properties and processing techniques available for synthetic polymer and natural polymer can enhance biocomposite material made of synthetic polymer and natural polymers. As you can see, is the problem statement that measured in this research. First is how does Aringa pinnata silicone biocomposite with different fiber composition react toward different diameter in compressive manner. Second, how does Aringa pinnata silicone biocomposite with different fiber composition react toward different height in a compressive manner. And third, what is the behavior of Aringa pinnata silicone biocomposite when exposed to this condition under the applications of compression using hyperelastic constitutive models. The objective of this study is to develop an accurate finite element model of hyperelastic component under compression based on explicit analysis, then to analyze the effect of fiber composition and cylinder parameter to the deformation behavior, stress and strain of silicone biocomposite material under compression. Next, to determine the optimum parameter using response surface methodology and design of experiment. Lastly, to predict the compressive behavior of silicone biocomposite material using artificial neural network. Scope and limitation of the project. The scope of study has been determined to be most appropriate for the mode of study for the research. The following are the scopes. A total of 34 samples are to be used for this study. They comprise of 5 different compositions, 3 different diameter and 3 different height. Second, pure silicone is reinforced with Aringa pinnata in accordance with its composition 5 fiber. Third, this study only focused on the compressive behavior of Aringa pinnata silicone due to different diameter and height. And lastly, the quantifying of material constant of the compressive behavior of Aringa pinnata silicone biocomposite is limited of 2 models, Neo-Hooken and Mani-Rivlin. Next, methodology. The finite element model was created with Abacus, a commercially available FEA software package with built-in failure criteria functions. Abacus was chosen because of its ease of use and ability to provide all of the functions required for analysis of hyperelastic structure. The current research was divided into 4 stages, which is Stage 1, mesh convergence analysis and numerical validation. Stage 2, setting up case studies using design of experiment. Stage 3, compression analysis. And Stage 4, optimization using response surface method. Mesh convergence analysis. Initially, in order to construct an accurate model, a mesh convergence study was undertaken to identify the appropriate minimum size of mesh to be used for the models. This procedure could reduce the cost of analysis while also ensuring that processing time is kept to a minimum. One model with 7 different mesh sizes were simulated under the constant compression load. The maximum stress on silicone rubber were recorded. Numerical validation. The findings from the Karimzadeh simulation and Hafizuddin simulation were compared and reported in Table 2. The percentage error of their difference were estimated and the error were fewer than 20%. This relatively mistaken implied that both simulations were dependable enough to be employed and confirm that my model were correct. For Stage 2, setting up case studies using design of experiment. Design of experiment is a field of applied statistics concerned with the planning, execution, analysis, and interpretation of control tests to analyze the factors that influence the value of a parameter or combination of parameters. DOE is a robust data gathering and analysis tool that may be applied to a wide range of experimental scenarios. After inserting factors inside the DOE, the total of simulation I have to run is 34 times, and from the simulation, 2 response will be observed, which is stress and strain. Stage 3. Compression analysis. What we want to analyze from the simulation are force, maximum stress, displacement, and strain. Force needed to compress the silicone rubber about 3 mm is now studied. From the simulation, we can see that the maximum stress to compress the silicone rubber about 3 mm is 31.67 Pascal. The diameter of silicone rubber is 5 mm. As we know, the formula area of circle is pi r square and the answer is 19.63 mm square. So the total force needed to compress about 3 mm of silicone rubber is 621.68 Newton. In conclusion, from the simulation, we want to analyze the factor of fiber composition, diameter and height of silicone rubber affecting the force, maximum stress, displacement and strain. Last stage is optimization using response surface method. From the simulation, the result that we collected such as stress and strain will be optimization using response surface method. All the value data that we produce in the simulation will be inside the blend table below after all the simulation completely run. RSM has a benefit in that it defines the interaction between independent variables and develops a mathematical model. The RSM approach investigates the link between input and output and identify the system of interest optimal response. Expected result. The expected result from this simulation is to analyze the effect of fiber composition and cylinder parameter to the deformation behavior, stress and strain of silicone biocomposite material under compression. Graph stress, strain and force displacement will be produced for every difference of fiber composition, diameter and height of silicone rubber that have been set up using DOE. From the graph, I will be analyze and compare the result of the simulation. Furthermore, the result of the simulation I also can investigate behavior of silicone rubber using Money-Rivlin and Neo-Hooken constitutive model. Preliminary result. Figure 6 show the graph of force versus displacement that were plotted directly from Abacus software. From the graph, we can see the force needed to compress every 0.5 mm of silicone rubber. Figure 7 shows the finite element analysis software Abacus is used to perform the finite element simulation of the polynomial N2 model on the silicone rubber according to the uniaxial compression experimental method. This polynomial N2 model only used to validate my model based on the Karimzadeh paper, but for my simulation, I will use Money-Rivlin and Neo-Hooken constitutive model because the value of coefficient of Money-Rivlin and Neo-Hooken constitutive model we got from the previous study about Aringa pinnata and put the value coefficient inside the property material in the simulation. Lastly, project planning. And this is the project planning, which is consists of title, project registration, FIP workshop, literature review, problem identification, methodology, convergence analysis, numerical validation, prepare project proposal, submit project proposal, and present project proposal for this semester. And for next semester, project planning is consists of simulate and evaluate the project and then prepare and submit the report. That's all from me. Thank you.